Hi dear students, I welcome you all. I am Dr. J. Chandrasekhar Rao, lecturer in physics from Government Degree College, Rajam. In the previous class, we learned about different kinds of motions and especially about simple harmonic motion conceptually and also experimentally. So, in today's class, we will derive the differential equation of simple harmonic motion and its solution. From the previous class experiments, we understood that if a body is in simple harmonic motion, then the restoring force is always directly proportional to its displacement from its mean position and also is opposite in direction. So, to derive the differential equation of simple harmonic motion, let us consider a body of mass m which is suspended to this spring. See here, and this is mass of this body and it is in simple harmonic motion. See here clearly, and the mean position of this mass loaded spring is, say here, this one, and it is one extreme position and this is another extreme position. So at any instant of time, the displacement of this body is, say, y. And also we know that according to our definition of simple harmonic motion, the restoring force F is always directly proportional to displacement of the body, that is, say, y, and it is in opposite in direction. So here we are taking as minus. So F proportional to minus y. So F is equal to some proportionality constant K into Y. Here K means restoring force per unit displacement and also it is called as force constant. And also we know that from Newton's second law, F is equal to ma. Here A means acceleration of the body. So F is equal to m into acceleration means rate of change of velocity, and that can be written as dv by dt. So that equal to m into d by dt of v. V means velocity and that can be written as rate of change of displacement. So dy by dt. So F is equal to m into d square y by dt square. So observe equation 1 and 2. From these two equations, we can write as m into d square y by dt square is equal to minus ky. If m goes to this side, then d square y by dt square is equal to minus k by m into y. Say equation number 3. Now let us take k by m as omega square. Then omega is equal to root over k by m. Here omega means angular frequency. So now the equation 3 will become as d square y by dt square is equal to minus omega square y. Therefore d square y by dt square plus omega square y is equal to 0. Say it is equation number 4 and this is known as the differential equation of simple harmonic motion. Now from this equation we can write as d by dt of dy by dt plus omega square y is equal to 0. Here we know that dy by dt means rate of change of displacement, so it is velocity. So this equation can be written as dv by dt plus omega square y is equal to 0. Now in this equation, in the first term, if we multiply and divide it by with the same quantity dy, then we get dv by dy into dy by dt plus omega square y is equal to 0. So we know that here dy by dt is velocity. So this equation will become as v into dv by dy plus omega square y is equal to 0. So that implies
V into dV plus omega square y dy is equal to 0, or V dV is equal to minus omega square y dy. Now integrating both sides, we get integral V dV is equal to integral minus omega square y dy. So this implies this is v square by 2 and this is minus omega square. Integral y dy means y square by 2 plus c. Here c is integral constant. So v square by 2 is equal to minus omega square y square by 2 plus c. Say this is equation number 5. When y equal to a, that means the displacement of the body from its mean position is maximum, then it is called as amplitude. So here the displacement y is equal to amplitude. Then here when the displacement is maximum, at that maximum position the velocity of the body is 0. So in the above equation, substitute in the place of velocity v equal to 0 and in the place of displacement y equal to a, then we get 0 square by 2 is equal to minus omega square a square by 2 plus c. So from this c is equal to omega square a square by 2. So this is integral constant value. Now substitute this value in equation 5. We get v square by 2 is equal to minus omega square y square by 2 plus c. C means omega square a square by 2. So this 2 get cancelled. So v square is equal to omega square a square minus omega square y square. That implies v is equal to root over omega square a square minus omega square y square. So that implies v is equal to root over omega square into a square minus y square. Therefore, v is equal to omega into root over a square minus y square. So this is the velocity of the body. But we know that velocity v is equal to dy by dt. So dy by dt is equal to omega into root over a square minus y square. So this implies dy by root over a square minus y square is equal to omega into dt. So now integrating on both sides, we get integral dy by root over a square minus y square is equal to integral omega dt. Say equation number 6. So let us consider left hand side of this equation, that is integral dy by root over a square minus y square. So to solve this, let us take y equal to a sin theta, and the differentiation of this one is dy is equal to a cos theta d theta. Now substituting these two values in this equation, we get integral dy. Dy means a cos theta d theta whole by root over a square minus y square. Y square means a square sin square theta. So integral dy by root over a square minus y square is equal to integral a cos theta d theta whole by root over a square minus a square sin square theta. Taking a square as common, so root over a square into 1 minus sin square theta, and we know that 1 minus sin square theta is equal to cos square theta. So root over a square cos square theta is equal to a cos theta. So here this a cos theta and a cos theta values get cancelled. So that equal to integral d theta, that equal to theta. So this is the left hand side value, and now substituting this value in equation 6, we get on left side theta and on right side integral omega dt. So here omega is constant, so integral dt, so integral dt means t. So theta is equal to omega t plus phi. Here phi means it is an integral constant, and also it gives the phase of the oscillating body. But from equation 7 we have y equal to a sin theta. So from this equation sin theta is equal to y by a, and this implies theta is equal to sin inverse y by a. Say this is equation number 9. And now substitute this value in equation 8, that is theta is equal to omega t plus phi. So on the left side, in the place of theta, we have to substitute sin inverse y by a, and on the right side omega t plus phi. So sin inverse y by a is equal to omega t plus phi. This implies y by a is equal to sin of omega t plus phi. Therefore, y equal to a sin omega t plus phi. So, this is the solution of differential equation of simple harmonic motion. So, dear students, in this class, we derived the differential equation of simple harmonic motion, that is d square y by dt square plus omega square y equal to 0. And the solution of that differential equation is y equal to a sin omega t plus phi.
These are certain references with the help of which I have prepared this presentation. You can also use these following books for your reference. The images and the video clips which I have used here, the credit completely goes to original owners. Thank you students. Thank you for watching this topic.